Morning. Everyone is awake, ready to go? Okay. So I guess you have me for the next 2 hours. So my challenge is to keep you awake till lunch. We'll see how it goes. We'll keep this informal. I actually have lots of slides, so I'll just go slow and see how far we can get. And again, you can stop me anytime. Just raise your hand and we'll stop. Okay. So what I'll do is I actually have 2 talks. The first one, can everyone hear me okay?
Yeah.
You hear it better? Okay. So the first talk is more of a sort of a review of fabrication methods. I'll show some of our work along the way in between and also at the end of this talk. But it is just to kind of go back and review maybe a little bit of what you're doing in the fabrication labs and some other methods of 2- and 3-dimensional fabrication of biomicro structures. And my second talk is going to be more focused on some of our research projects on different types of biosensing platforms that we are working on. All right. So first of all, I want to thank all our group members and all the collaborators that have kind of been that we've been doing the work with, and also the funding agencies. So this is our group, postdocs and grad students and collaborators. And the reason I want to show the list of collaborators, this is in the last like 4 to 5 years or so. I just want to show that this field is certainly very, very interdisciplinary. And you can see that collaborations from people from medchem to food science to med school and so on and so forth. So again, this is I think the excitement in this field is the fact that it is very interdisciplinary and you need to work with many people to be able to move the field forward. Okay, so fabrication of structures, which is really the focus of this talk, is really sort of very originally motivated by this plot. Does anyone know what this plot is called? What is this law or rule called?
Moore's law.
Yes, the Moore's law. So Gordon Moore from Intel predicted this, or actually sort of put that as a challenge for the microelectronics and semiconductor industry, that can we, shrink the chip size and the minimum dimension every so often. And it turned out that ended up being that you basically every technology generation, the minimum dimension, which is the channel length, becomes L. Then the next generation is scaled by L over square root of 2. And that doubles the number of transistors on the chip. And that has happened for every about 18 months or so, about 14 to 18 months, every 14 to 18 months. And that's called now Moore's law. So the minimum feature size on a silicon chip has dropped exponentially. This is a log scale here, so this drop is exponential as a function of time, as a function of years. And in 2010, now we are certainly in the 20 to 30 nanometer range on a full 12-inch wafer, silicon wafer. So it's pretty amazing. It's one of the most amazing technological advances ever. The fact that you can make this 12-inch wafer and have a lateral dimension control of about 30 to 40 nanometers. So that's certainly very amazing. And of course, this has been continuing. We'll see what happens in the future, whether this can actually continue and how far this can continue. But the chips have become denser and denser, and the actual fabrication processes and the back-end metallization is very, very complex. So this is just sort of how things started out, and of course they're continuing on in microelectronics and nanoelectronics. But if you also then look at on size and scale of different objects, you look at the biological things that are around us that I would call are fabricated using bottoms-up fabrication technology. So these are all biological things. Most viruses are in the few tens to 100 nanometer range. Proteins are smaller than that. You can go up, of course, in bacteria are a few microns. Plant and animal cells are in 10 to 100 micron range, and so on and so forth. We have the structures that are synthesized by bottoms-up chemical methods. You saw some example in the earlier talk, and also maybe last week. Things like carbon nanotubes, quantum dots, nanoshells, nanowires, and so on and so forth. And of course, what I just mentioned, which is this microelectronics-inspired structures, which we call top-down fabrication, where in 2010, the minimum feature of a MOS transistor is something in the order of 25 to 35 nanometer. This is the actual gate length, right? So using these top-down fabrication methods, we can also make nanopores, which are just about the same diameter as the diameter of DNA, and so on and so forth. So this is a very exciting area where you can now combine this microelectronic fabrication. And then what happened was about 25 years ago or so, maybe about 30 years ago, some researchers that were working with microelectronic processing also thought about making MEMS structures, right? So the idea that you can use the fabrication methods to also make structures that can move, that can sense or actuate. And that led to the whole area of MEMS, which is micro-electromechanical systems. And then BioMEMS is really the biomedical or biological applications of MEMS. So one more just historical plot, and then I'll move on. So if you look at from the 1900s, we had the vacuum tube technology that changed the world at that time. Then the transistor was invented, semiconductor technology came about, led to all the revolution of the internet and other things. And then the question is, will nanotechnology have some sort of a similar impact or not? And we have to separate the hype from the reality and focus on useful applications. But nevertheless, there's a lot of possibilities and potential. And nanotechnology is really an enabling, pervasive technology that's going to impact many fields. And I think we are certainly very excited about the intersection of nanotechnology with modern biology and biotechnology and medicine to result in personalized diagnostics and therapeutics, applications in synthetic systems biology, and also hybrid devices and tissue engineering. So there's lots of interesting things when you put micro and nano with bio together. And things like diagnostics, therapeutics, tissue engineering, micro devices for cell biology, bio-inspired materials, bioelectronics, biofabrication. So there's really lots to be done in this general area of biosensing, bioactuation, especially at the micro and nano scale. Right? So BioMEMS, you might have heard this word before, but it stands for biological or biomedical micro-electromechanical systems, and bio-nanotechnology, of course, is sort of the biological applications of nanotechnology. So what I'll do is I'll give you kind of a background of this fabrication also, and this would also, I think, correlate well with what you're seeing and what you'll be doing in the lab modules also. So we talk about fabricating MEMS and NEMS silicon structures, let's say, and these are, like I said, certainly these fabrication methods are pretty much all microelectronic or silicon fabrication inspired, and then other things that have been added to it that I'll show you. So using these fabrication methods, you can form structures that could be used to form sensors and actuators. You can process signals that are not only electrical. See, chips were chips were used only for processing electrical signals. But with MEMS devices, you can also process non-electrical signals, such as mechanical or chemical or other things, or optical. You use conventional semiconductor processing techniques and some new fabrication methods that are maybe more unique to MEMS fabrication. So there's certainly the standard things like etching, deposition, photolithography, oxidation, epitaxy. You can use all of those, and things like deep reactive ion etching, or metal plating, or polymer or PDMS processing that we'll talk about. Okay? Then another two terms that are often used in MEMS fabrication is bulk and surface micromachining. How many of you have heard those terms before? Bulk and surface micromachining. Bulk micromachining. No one? Okay, so no one is really taking a fabrication class here. How many have taken a fabrication class before? No one is taking a fabrication class. Right, okay, well that's good. Then I'll give a little bit of this overview. That's useful. So it's interesting to assume that everyone has seen that, and we might get into how structures are made. Okay, so let me just show you some basic micro fabrication processes. So you might have a silicon substrate. Okay, that looks like this is a cross section of the silicon substrate. Then you might use different deposition or CVD, chemical vapor deposition, or oxidation processes to form films on both sides of this wafer, for example. Then you could use a photomasking process to form a photoresist pattern and then etch away this material selectively. There are chemistries available. For example, hydrofluoric acid HF will etch SiO2. Other chemical etches would actually etch polysilicon and so on and so forth. You can use nitric acid or phosphoric acid actually to etch silicon nitride. Then you can also use that region as a mask to then etch the silicon using chemical etchant or gas phase etchant. So you can form structures that have some physical size and shape, and there's lots of well-defined chemistries you can use. You can take this as sort of a toolbox, a recipe box, and build these structures. And then you have to be in the right order. The sequence of these steps has to be in the right order for you to get the structures you like. You can form another photoresist mask, and you can remove this material again, and then now you can use what's called a deep reactive ion etching to etch a deep trench in the silicon wafer that has a very high aspect ratio. Might be a few microns wide and tens to 100 microns deep. you could form another opening here, for example, and now you could change the conductivity of the material. You can dope it with, for example, phosphorus or boron or arsenic, and you can change the electrical properties of this region, and you can also change its chemical properties so that now this region will be selective to etching by certain chemicals. So then you could open a backside opening here and then etch this entire region, stop on that layer, and form a very thin membrane. So you can form structures like this using silicon MEMS fabrication. And this kind of processing is typically called bulk micromachining because you're kind of handling the back of the wafer and the front of the wafer. You can also do what's called surface micromachining, or maybe more of things like additive and subtractive processes by putting films on both sides of the wafer. Then you can have these openings you can etch this oxide using hydrofluoric acid, for example. You can deposit another thin film, let's say a metal layer, this could be gold. You can then actually remove this region from underneath by side openings, and I'll show you pictures, and make this layer a suspended layer. So now it's suspended. While it is anchored at these two ends, this region is suspended. Then you can use this metal and then deposit a photoresist mask shown here and actually form these regions, and then use the metal as a mask for electroplating and plate gold, for example. The color didn't show, right? But you can plate gold, for example, and remove the photoresist now. So now you end up with these regions, which are these gold structures on a suspended membrane. So you can do lots of things in terms of fabrication and make these three-dimensional structures. Okay. So let me give you some examples of what you could do with things like this. So you can make these structures to do pressure sensing, for example. So you can make a pressure sensor on a chip. And these things are not commercially available, actually. So for example, you can make a structure that has a central mass, some sort of proof mass, and then this mass can be suspended by two very thin beams. And these thin beams, then essentially what happens is now if you apply some pressure on the structure, then the structure would bend. And these regions right here bend, and there is essentially, if you put a resistor in this region, then there's a property called Piezo Resistivity, and the resistance changes with stress. So now if you were to be measuring the resistance of this region, it will change, and that change in resistance indicates that mass has moved, either due to some pressure or due to acceleration or deacceleration. So that would be a piezo-resistive sensor that you can make on a chip. You can also make things like capacitive sensors, where, for example, you can make this thin membrane that I showed you earlier on a chip. You can put a thin metal layer and then have some sort of a cover, again, a micro-machined glass or silicon cover, and now this becomes a capacitive sensor. You have a capacitor with an air gap. And when this membrane, which is very thin, bends, then the capacitance changes, it's connected to a circuit, and now you can measure capacitance by changing capacitance and hence change in pressure. So this becomes then a capacitive pressure sensor. And these things are, you can make them on a chip, you can make lots of them, and these things are being commercially used now. So let me give you some examples in this picture. So this is actually well over just about 10 years old, and there's many examples of this. This is a bulk micromachine accelerometer that measures acceleration or deacceleration. And these type of devices now are in all the cars, as a matter of fact. When you slam on the brakes, the sensor that detects that acceleration or deacceleration is some sort of a MEMS type of a sensor, micro-machine sensor, that then actuates or sort of deploys the airbag. So in this case, this is a chip that might be, let's say, a centimeter on the side. You have the central proof mass, and then you have these very thin, you have a thin membrane region that goes around. This is the thin membrane region. And then the resistors are placed here. There's one here, one there, and one there. There's a fourth one on this side. This is a cross-section. So this is set up as a Wheatstone bridge, essentially, and this becomes a proof mass with the resistors here, and it becomes a micro-machine accelerometer in this case. This is a tip for an AFM. I think anyone who's done some nano fabrication or nano characterization has probably heard or seen AFM. This is about a few hundred microns long, maybe about 10 to 20 microns wide, and it has this very sharp tip, where this tip essentially scans over a surface, and you can get, certainly close to atomic scale resolution of surfaces using variations of an AFM, essentially other scanning probe techniques like scanning tunneling microscopes, for example. But the concept is the same, where you have this probe, and this is fabricated using MEMS fabrication. Okay. Most of these projector, I think this one probably too, I'm not sure, but most of the smaller projector have this DMD chip from TI and from other companies. This is actually a Micromirror Display on a chip, essentially, where you have a chip that has these mirrors that move. So each one of these pixels is a little, you call it a mirror, but it's really essentially a metal layer that can reflect light. So this is a microfabricated structure where each pixel is maybe about 10 to 20 microns on a side, and it's anchored at these two edges, shown, for example, here as a schematic. And what you do is you actually feed your signal, right, to this, you actually shine the light on the chip with some filters, and you feed your signal digitally to the chip, so that essentially the mirror is either on or off position, and you can move that electrostatically, and you can get the light to go to the optics and then project it. So most of these big displays now are using this digital micromirror display, which is a MEMS device. It is a chip which has these mirrors, millions of mirrors that can be addressed. Okay. This is some more examples of, this is a chip with a bunch of circuitry and an accelerometer. Again, but this is a surface micromachine accelerometer, where in this case, the actual sensing is taking place by a lot of fingers. These are polysilicon fingers that are fabricated like this and then released. So when the lateral capacitance changes between the plates, then the chip in the system knows that it's been accelerated or deaccelerated, and that is then used to process the signal for the deployment of the aircraft. So this is a single chip accelerometer with the circuitry. This is actually a single chip microphone. This is a project I was involved in when I was at National back a long time ago. Essentially, this is a microphone is nothing but an acoustic transducer, right? It measures air pressure. So what you do is you make a capacitor. This is a chip where the top plate is this gold. This is a thick gold back plate that has a lot of holes in it. So it's been plated using a photoresist mask, and you can make a connection to this plate. And then if you flip this chip over on the back side, you will see this, which is essentially a trench, this etch cavity that's been etched down, and then you have a silicon membrane that's connected to the substrate by these 4 spring regions right here, 1, 2, 3, and 4. And this membrane can then move up and down, and essentially there's a capacitor. So it's a capacitive pressure sensor that can be used as a microphone on a chip. Okay. So these are examples of MEMS devices. And then there's been lots of examples of, there's an older slide I updated, but essentially there's been lots of examples of then using of these MEMS devices for biomedical applications. So University of Michigan has Ken Wise group has been working for many years on making neural probes. You make silicon probes with electrodes on it that you stick in brains and record electrical activity. This is another neural probe from a group at Stanford from some time ago. Greg Kovacs's group. So here again, there's electrodes right here at these openings that you see here. And these are long needles that can be stuck into tissue. This is an array of transistors, field effect transistors, MOSFETs, with cells grown on it. This is neurons that grow on it, and essentially you can try to couple the electrical activity of the neuron to the MOSFET and sense the electrical activity using FETs. This is a micro needle by a company, Kumitrex, that was trying to commercialize it. I'm not sure the status of this, but this idea of a micro needle or a nano needle has been very attractive, where the basic idea is that if a mosquito bites you, like it did last week when we were playing volleyball, you don't feel it at that time necessarily, because the size of that needle that the mosquito is putting into your skin is smaller than the size of the cells and the pain receptors. So at that time you don't feel it. So if you can replicate a very small needle with a hole through it, this could be used for drug delivery devices. You can have a patch with these needles and deliver drugs without the person feeling any pain. So that was the idea, and I think there's been now some companies trying to commercialize this general idea of an array of nanoneedles or microneedles for delivery of chemicals. This was a biochip that I was involved in developing, which could concentrate bacteria and then grow the bacteria inside this microfluidic chip and then detect the growth electrically, and I'll show you examples of that later. And this is an array of cantilever, which are these resonance sensors or stress sensors, and I'll show you examples of that also in the next lecture, which can be used for the detection of biomolecular activity. So these are examples of MEMS structures that have been used for sort of bioelectron applications. Okay, so for biochip and biomems, silicon is certainly very useful, silicon and microelectronic materials, but then there's also other materials that people have used using those techniques of fabrication, but then expanding it to other types of materials. So materials such as glass and quartz, they're very useful because they're transparent, so you can do optical detection, you can do fluorescence, and things like that. Silicon is not transparent except in the infrared range. Also polymers, so different types of polymers have been used, such as PDMS. This is what you are using in your lab, in the lab modules. You can also use PMMA, Teflon, and other types of materials. And actually, as a matter of fact, why should you be restricted in the types of materials you use? You should be able to use anything. So people are using even molecules like DNA and proteins, and even things like cells to actually fabricate structures. Because certainly we are fabricated out of cells. So why couldn't you fabricate other structures with cells? So certainly you can also use biological entities, and this is absolutely also a frontier of biomems and synthetic biology. So for biochips or biosensors, in addition to silicon, biocompatibility is very important. So you need that for maybe implantable devices or devices where you're going to introduce a sample and you don't want the sample to be impacted negatively by your chip. You would like it to be transparent in the visible spectrum, so that's where glass and quartz and some plastics can be very useful. Rapid fabrication. The fact is that silicon devices take a little while to fabricate. You have to go through many steps, and you can't, some steps just take time, and you have to go to a clean room, and it's expensive. So if you can certainly do some sort of rapid fabrication or rapid prototyping, that would be very useful. You want the materials to be photo-definable, chemically modifiable, so you have these possible choices that I mentioned earlier. So the alternate fabrication methods, I'll briefly review these methods and show you actually our work mainly in the area of 3D lithography, actually 3D structures, but hopefully I'll get to that in this lecture. So this is mainly a review, and I'll show you our work at the end. So soft lithography really came from George Whiteside's group some years ago, and now it's used a lot in replication and molding and micro-contact printing, and I'll show you examples of that. So these are different versions and different variations of soft lithography. Then also you can talk about compression molding, and compression molding really comes from sort of the mechanical engineering side of the house in terms of being able to fabricate structures in plastic. And those methods have been miniaturized, and actually nano imprint lithography is really a nanoscale version of compression molding. And then I won't talk about inkjet printing very much today, and I'll talk about steel lithography. So this idea of replication and molding, the way it's a simple idea, but it's really very powerful. The idea that you can make a master mold from silicon, glass, metal, or SU8. These are all microfabricated or materials that can be microfabricated. So you can make structures like this, for example, the silicon wafer with some pattern on it. And then you do the surface treatment of this master. You pour for example, the PDMS, and I'll show this chemistry a little bit more in more detail. And then you cure this, and then you peel off this PDMS structure, this material, and now you can essentially use this back to this mold, this master mold can be used again and again. So you make the master one time, you pour the PDMS, you do the surface treatment, you pour the PDMS, then you cure it, and then you peel it off, and now you have a polymer structure in PDMS with some pattern to it, some features here, that then you can use to do other things. You can use this to make a microfluidic device, or you can use it to do stamping of proteins, and then you can go back and use this master again and again. So that's the idea in this application of molding. Okay? And it's very easy to use. You can use it. You can do it sort of almost anywhere, especially if the structures are not nanoscale. You still have to be careful with the surface treatments and all that. But this is a very easy process, and you are doing this, or you use part of this in your labs, right? So PDMS is polydimethylsiloxane. It's an elastomer that will cross-link chains. It will dissolve and it will decompose before melting, and it must be polymerized. So this is sort of the chemical structure for it. It can be used to perform rapid prototyping using a master that you can make with silicon, metal, like metal on silicon, or deep ROE of silicon, or SU8 on silicon. Fast, easy fabrication of microchips, irreversible bonding to other PDMS glass and silicon devices. It's optically transparent down to 230 nanometer, which is very useful. And one of the products available is the Silkguard 184 from Dow Corning and other also. So you actually take this commercial PDMS, which is a base and a curing agent, which is a base and a curing agent. The curing agent has this platinum-based catalyst that adds this SiH bonds across the vinyl groups and forms these linkages right here. So then you can have this three-dimensional cross-linking that occurs. And essentially, you can also control the stiffness of the material slightly by controlling the ratio of the base to curing agent and get a material that's more cross-linked or less cross-linked. So you can make structures like that. And then you can use that structure, that PDMS structure, and you can then use it to micro-contact print proteins or DNA or other chemicals, other molecules. You can ink the PDMS structure with molecules such as proteins, DNA, or volatile files. It's very much the idea of taking a pen, in the olden days, and dipping it with an ink, and then writing the ink, essentially transferring that ink from the pen to the surface. That's basically what you're doing with these structures. Transfer the layer through physical contact. You have to optimize the time and the temperature and the humidity and the ambient around this. So there's lots and lots of papers on all of this. I'm just giving you a very brief overview. But you can transfer that layer through physical contact, and you can also have a layer such that the molecule that you're putting actually forms a covalent bond with the substrate. So that you can transfer that and possibly form a covalent bond with the substrate. And you can, theoretically, you can do this on flat surfaces or on curved surfaces, this stamping. And this could be done then on other plastic surfaces. And there's lots of literature on this. So you can make microfluidic devices with this idea of this PDMS, pouring the PDMS on structures with patterns. So for example, you might take a cyanidized silicon mold, put a PDMS layer on it, and then cure it. Then you might take another physical structure, like even a little Teflon tube, for example, and use that tube as a mold, essentially, and then put a second PDMS layer, and then now you can pull this tube out, and you'll form a channel. You can even close the end of the channel by putting a little bit of drop of the PDMS and seal that. You can form vertical channels. We often do this by actually putting a PDMS around a Teflon tube that's vertically attached. So you can have a chip. You can put a tube vertically on it, put PDMS around it, and you can form a vertical channel. And you can put multiple layers like that to form channels that have like an angle. So you can do some very interesting fabrication this way, and then come back and put tubes on the PDMS, actually stick it in to form the inlet outlet. And you can make structures like that. So this, for example, is a silicon chip underneath, where you can see some patterns underneath with metal. And there's actually 3 layers of PDMS. This first layer is here. There's a second layer here, you can see, that's slightly offsetted. And then there's a third layer right here, which is a much thicker, which is just basically a little reservoir. Essentially, that structure was made by putting a PDMS around the tip of a micropipette. So you can see that shape. So you put a fluid structure here, you can put a cap on it and suck the fluid through this one by pulling pressure. And the fluid will go through the channels there and go back. So you can have the fluid go through another fluid. This is another one, which is a glass base and 3 PDMS layers with a top input output port, and also it has valves actually. So this is the cross section of this chip, where this is this tube, and then inside it has multiple layers from the channel like that. That's a cross section of this chip. And this is actually a cross section here in here, where what you can also do in these kind of devices, and this was really pioneered by Steve Quake at Stanford, where they did it in very large, dense arrays. But you can also push air through these channels, and because the material is flexible, when you push air, it actually will bend, and you can form valves. So you can then actually close and open valves, and you can seal this region, for example, or you can, of course, when you push air sequentially, you can pump fluid. So you can make pumps on a chip and move fluid using devices like that. Okay, any questions? Make sense? Okay. So another sort of a nanoscale manifestation of this stamping or the micro-contact printing. It was called dip-in lithography or dip-in nanolithography. We have a system here upstairs on the third floor here also. You can ask Larry to show you that if you're interested. In this case, you actually use an AFM tip that's used to write molecules. So essentially, that tip that was micron scale or larger for the micro-contact printing, if you make it nanoscale and use an actual AFM tip, that really becomes what's called the dip-in lithography. And there's a couple of companies now that sell this dip-in nanolithography tool. One of them is Nano Inc. You can put SANs, DNA, and proteins. Right now it is serial, which is you have one tip at a time. So this process is serial. You actually ink it, and then you go and you write. But there's been efforts on trying to make many cantilevers in parallel and also possibly provide a continuous source of liquid by putting microfluidics in the tip to provide the actual solution. But you can make, with this, you can write structures that are in the certainly, tens is still hard, but maybe hundreds of nanometer dimension is certainly doable with this, but it is a serial process. Okay, so it's really, it's possibly good for putting molecules down on the surface of DNA and proteins. Okay, compression molding. So this is something that is actually used today. One of the most common examples of this is your CDs, right? Your CDs are made by this process of molding, injection molding. So it's precision, the precision injection molding, where essentially you have a master mold and you put plastic around it and you cure it and you pull it off, and it's a very intricate process. But essentially, you can use a metal mold and put plastic parts and make plastic parts around that metal mold and make lots and lots of them. So you can actually make, with the precision injection molding, you can make features down to 0.1 microns, 1,000 angstroms, and as wide as 0.6 microns. And this is used for the CDs, actually. Also, any of these plastic cartridges that you see, which might be used for biosensors, or anything that's plastic around you that has any patterns, is made with injection molding, whether it's precision or not. So this idea of hot embossing has also been around, where you take a mold, again, and then you have a thermoplastic material, some sort of polymer, and you heat the whole thing up. The polymer actually will become more fluid, and then essentially you apply some pressure, and this mold is essentially pressured in, and you can form the patterns in this thermoplastic materials by this mold, and then you can pull this out. So that's called hot embossing. So nano-imprint lithography, which also is a tool up inside the clean room. When you take a tour inside, you can ask to see it. That's really a nanoscale version of this hot embossing, where now what you do is your master, you make that with e-beam lithography and etching, and if you can make your master to have nanoscale features, then you can replicate those nanoscale features onto another polymer link, essentially, which is your photoresist. Okay, so nano-imprint lithography was really, and Steve Cho from Princeton originally came up with this, started a company on this, and has patents on this idea, which is really a nanoscale version of hot embossing. So you make your master first. This right here is metal pillars that might be made with e-beam lithography. So that's expensive, but you make it one time. And then you can imprint this into, so for example, here are the 10 nanometer diameter holes that are imprinted in PMMA, and you can see these holes that are essentially a mirror image of these pillars. Okay? And then using this as a photoresist, now you can deposit metal in these holes and remove the photoresist and form these metal dots. So these metal dots can be patterned using this process. Okay? So this is a nanoscale extension of hot embossing. It needs a nanoscale master mold. And this technology has been added to this international technology roadmap for semiconductors. But it's really hasn't taken off as much as you might expect for a variety of reasons. But it is used because the silicon industry, has so much momentum behind it, and they've just done such a good job of pushing the deep UV lithography that actually this really hasn't this is not necessarily out yet, but it is on the roadmap, and it is being used for specialty applications. The tool we have here in the clean room is a nano imprint lithography. It's called a step and flash. So this was a modification of the previous process. In this previous process, the mold, this master, is not transparent. It's some sort of a structure like a metal or silicon that you cannot put light through. So the idea here for step and flash is that you can actually, if you make the mold transparent, then you can actually shine light through it and UV polymerize your resist underneath it. So what you do is you dispense a bunch of drops. There's a system that dispenses small drops on the surface, and then there is your master which you make separately, and this master now is in quartz. So it's a quartz transparent mold, and you define your features on that first. Then you lower this template and fill that pattern, and then now through this transparent mold you shine light, UV, and you polymerize your resist, and then you separate the template from the substrate, because now it's not liquid anymore, it's been polymerized. And this now becomes your photoresist to do etching or other subsequent patterns. Okay? So this system has the ability to align the template to features on a wafer with less than a micron, about a micron or so, maybe half a micron. So that's not that great, but that can be improved. But that's what commercially is available now. Wafers up to 8 in diameter can be used. And the template size is about a centimeter by centimeter. So about a centimeter by centimeter template that then you step and flash. And that's why it's called step and flash. You have a template that you step. It's about a centimeter over a whole 8-inch wafer. So you step it, you flash, then you move over, step, flash, and so on. So that's why it's called step and flash. And in between, you have to put this liquid down, which is the system does it automatically. So this is one of the new technologies for nanosplit patterns. Okay. All right. Let me switch gears a little bit, and the rest of the time talk a little bit about the surfaces and chemicals and how do you attach molecules to surfaces. Give you a little review of that. So you've heard this word self-assembled monolayers probably multiple times through these 2 weeks. So SAMs, self-assembled monolayers, these are ordered molecular assemblies that form spontaneously, which means that the lowest energy state for these molecules to form is a monolayer. Okay? And these typically might be some sort of organosilane or an organosulfur layer. So for example, you might have typically some sort of a called RX3, where R is an alkyl chain and X is a chloro or a alkoxy group. So that group, this X essentially, this X would bind to the substrate. Okay, so if you have, for example, a silicon dioxide, then you can have this alkoxy group that actually bind to the silicon dioxide or glass, which is the same thing, or an oxide. So essentially, the organosilanes are used to attach DNA or proteins to any sort of oxide. So for example, SiO2 or aluminum oxide or glass, which is a form of SiO2, you use an organosilane as your molecule to attach to the substrate. Okay? And on the other end of this, you'll have for example, this alkoxy group, and then you would have some sort of a certain carbon, this alkyl group, 6 or 12 or whatever. And then on the other end, you might have some other group, such as an amino group or something else, that you can do other chemistry to attach a protein or DNA. Okay? Actually, you might then put a glutaraldehyde group, and then a glutaraldehyde molecule, and then a protein or a DNA. If you are working with gold, then you'll always use some sort of an organosulfur. So sulfur is known to bind to gold very strongly. So then in that case, we have these alkane thiol molecules, some length of this molecule R, but then you have an SH, this is sulfur, hydrogen, the hydrogen comes off, and the sulfur would bind to gold on the surface. So if you're working with gold, you'll find tons and tons of papers that talk about attaching DNA or proteins or SAMs essentially to gold. So with gold, you always use this organosulfur, most always, and then for oxide, you use silanes. And then this is used to immobilize oligonucleotides, proteins, antibodies, etc. So let me just go through that a little faster. We'll skip some of these slides, but essentially, this is work that we did where we used different linkers by vapor phase deposition and use monofunctional silane. Typically, people have used this tri-functional silane always, where you have a molecule with 3 legs essentially, and those 3 legs is what attaches to your SiO2 surface, and then on the other end, then you do chemistry to attack something else here. But with these 3 layers, there is some issues, and there's a sort of literature. I mean, you can get it to work, but it is more problematic and it's not as controlled. And this, if you don't do this right, then you can form multi-layers. So you don't form a self-assembled monolayer in this case, but you can form multi-layers. A lot of people have reported these problems. So we actually used a mono-functional alkoxysilane, and we compared it to the tri-functional silanes also, and with this monofunctional silane, we can form very nice thin sands. You can see that these layers, this is thickness of the layer measured by ellipsometry, that after a certain amount of time, these thickness saturates to about 12 angstroms in this case, 11 angstroms in this case, and about 8 angstroms in this case. So we are forming SAMs, self-assembled monolayers of this. This is a vapor phase process, so you end up using less material. And then you can then go on and attach the proteins to it too. You can then pick your other molecules, such as the fluoraldehyde, or this BS peg, essentially, which is a peg with 2 groups at the ends, or this thing called DSC, and then attach a protein to it. So there are these chemistries that are in literature that you can use and optimize it for your application. But we've been using this vapor phase deposition of the monosilanes and then attaching proteins to it for different applications. You can also then, like I mentioned earlier, if you have gold, you can do DNA. So this is also, you can think of this as a way to do fabrication, where this was work done a long time ago with nanoparticles in solution from Chad Merkin's group, where they took gold nanoclusters and functionalized each gold particle with the layer of DNA. You heard a little bit about DNA this past week. Everyone knows a little bit about DNA, some a lot, some little. But a DNA molecule, you can get a short strand and get another strand that's complementary to it. You can take this strand and using this chemistry that I just described, you can attach that DNA to the gold particle. And this is showing one, but you have many of them. So now if you mix these 2 types of particles with these 2 different strands, and actually possibly a linking strand, then you can form organized clusters of these gold nanoparticles that might be useful for some optical applications. Okay. Now, when we make biosensors, a lot of times we want to detect proteins, and earlier Logan talked about different types of kinase and different proteins and other things like that. So certainly the antigen and antibodies are very central to biosensing. They're complicated, they have complicated folded structures. The actual binding between the antigen and the antibodies takes place through multiple types of interactions that includes hydrophobic, hydrogen, ionic, van der Waals. You can also use the system called avidin biotin. This is very commonly used actually in microbiology and cell biology and also in biosensors. Avidin biotin can be used to link different molecules. So you can take, for example, biotin, and you can conjugate this biotin, which is a vitamin actually. You can conjugate this to a molecule like DNA, and then avidin is a larger protein. This is here shown as just one subunit of avidin with the biotin layer. And this avidin then can also be linked to other molecules. So this avidin-biotin linkage is very commonly used, and it's used as a kit essentially to bind 2 different things together. There's a very strong affinity between avidin and biotin, and you can also use this to attach molecules to surface. So something that we had done before is take oxide surface, use a BSA, which is bovine serum albumin, which is a protein essentially, bovine serum albumin, and you can get the BSA to be biotin-related. So you put a BSA with a biotin on the surface, then you put in avidin, which has 4 binding sites. One of them binds to the biotin, and then you can bring in a biotin molecule and bind that to the avidin. So essentially, it's like a lock and a key type of mechanism almost, and you can get these molecules on the surface for various applications. Okay. This is an example of actually detection of DNA using gold particles on a surface. So I can take a surface and can have a capture probe of DNA that I attach in this thiol chemistry. And then you can have an avidin-coated polystyrene beads. You can have a biotin biotin molecule here. And essentially, when you have the right sequence, then this biotin molecule will bind to this capture probe. Biotin DNA would actually bind to this, and then if you put in these beads, then the avidin will bind to the biotin. And here you can see that actually when you have a control where the beads are not supposed to bind, you have very few or no beads, but then you can see on these gold dots, lots of beads in this space when you have the right complementary sequence. So things like that could be used and have been used for sensing of DNA molecules, essentially, that form the linker in between a larger structure and the surface. Okay, let me go through. I have many more slides to come. So micro-contact printing can be used to put proteins also. So in this case, you can make this masker, as we showed earlier. This is just making the masker. Then you take the PDMS. This is the PDMS. In this case, we're putting fibronectin, and you can incubate this with fibronectin and then stamp that on a glass slide and form these patterns of fibronectin. You can also add this boronic F12 to prevent cells from binding. And you can form structures. So this is actually the maskers with lines of 10, 15, 20 micron with gap 50 micron. And this is different gaps. These are circular patterns. And this is the pattern protein. You can actually then stamp this protein, this fibronectin lines of, this actually, sorry, it's BSA actually. This is fluorescent labeled BSA, but you can also do different proteins like that. These are lines of BSA. You can also make circular patterns of BSA. Then we also put cells on it. And in this case, actually, these are C2, C12 muscle cells. These are skeletal muscle cells that then get aligned to those patterns that we transferred and stamped. And you can even get the cells to grow over time. And we are now actually working on trying to see if these C2, C12 cells will actually become myotubes and actually contract or expand or actually show some twitching. Okay, let me show you then a three-dimensional method. So everything I talked about up to now was actually semi-two-dimensional. You can make three-dimensional structures using MEMS processing. I mean, structures that overhang or structures that are vibrating, right? But what about polymer three-dimensional structures? So one technique that we have used is a technique called stereolithography. And this, again, is used now to make plastic prototypes. This is a commercially available technology. And it works as shown here. You have actually some sort of a liquid photopolymer in a bath. And then you have a platform. You do a CAD drawing of your structure that you want to build. And then there's a laser that would come in, and depending, guided by this CAD drawing, by what you drew, the laser will raster and scan and polymerize the layer, and then the stage will move down, and then it'll polymerize the next layer, the stage will move down, and then you come back and polymerize the third layer. So you do a layer by layer polymerization, and you can make three-dimensional structures this way. Of course, there is some limitations to this, obviously, and there's issues of resolution and all that. So these are commercially available systems. We have one upstairs here in this building that we have modified to do bioapplication, essentially, with this. So we took this system and made a smaller bed, a smaller bath. This system has a wavelength in this range. We are using this SLA 250-50. It's a 325 nanometer wavelength. The XY resolution is actually better than that. It's about 100 microns or so, 150 microns. We've optimized that. And the Z resolution is also about 100 microns. So the XY and Z resolution is about 100 microns. So what we have done actually is adapted this process to work with cells and hydrogels. And we have used PEG, polyethylene glycol, PEG DA, polyethylene glycol diacrylate, with different molecular weights. We have worked with 700 all the way up to 10,000. Essentially, that's the length of the molecule in Dalton. We use a photo initiator. This Ergopure 2959, that's the commercial name for it. That's the chemical name for it. I won't try to pronounce that. And essentially now the idea is, the bottom line was, our goal was in this case, can you put cells in these polymers and use polymers that are biologically compatible and actually make structures, soft structures of polymers that have living cells in it. So that's the goal. And you can make three-dimensional structures that way. So the way then this would work is you have a solution with cells, and you want to now make sure the free polymer doesn't affect cells, the cells can stay alive, and the cells can survive the laser process also, the laser also. Okay. So we've been able to actually optimize this and get this to work. We can pattern the hydrogels in 3Ds. For example, if you make structures like this is a CAD drawing of a structure with these 3 spokes, and this is the actual polymer part that comes out. It's about a centimeter on the side, so it's about a centimeter, 10 millimeters or so. This is a structure that had some ridges, and it had this curved region. You can see this, let's translate a little bit. You can see those ridges there. And you can even make structures like that, essentially. Anything you can find a CAD drawing. There are some challenges in making structures that overhang, but you cannot make too thin structures that actually have an overhang. But if they're thicker, a few hundred microns, you can make overhangs also. Okay. So the nice thing about this now is we can also do what we call a bottoms-up stereolithography, where we adapt this to use with multiple cell types and with possibly different material composition. And that can be very, very useful for tissue engineering applications and some bio applications. So in this case, the idea would be that you put a solution, you actually inject solution with cell type A, and then polymerize it, and then move the stage down and put cell type B, and move the stage down and put cell type 3. So then you could do different cell types. Okay. And there's a couple other groups working on this approach, but we've actually been able to get it to work and optimize it, and as I'll show you some cell biology results. So we can make structures like this. These green and red, these are actually fibroblasts that were labeled with fluorescent dye, green or red. The red has actually diffused out a lot, but it seems almost continuous, but that's because of the imaging. But essentially, these are then 2 different cell types and 2 different layers. So we can put in red colored fibroblast and polymerize that and form these structures, these overhangs, and then do it with green labels from green fluorescent cells. So it's 2 different cell types. And you can see a cross-section here with the red, green, with a spacing of about 100 microns. So you can make structures like that, essentially. This is the hydrogel structure, and this is the top 3 layers and the bottom 3 layers, slightly out of focus, a little bit below. And these black dots, or this region, essentially a dye to look at cell viability. So the cells are then viable in these structures. Yes, please.
Are you able to maintain flow within these structures?
Sorry?
Are you able to maintain flow within these structures, or is it still?
No, so this is actually just sitting in a little vial or a little beaker. So there is no active flow around it. But you can absolutely put this structure in a perfusion chamber or in a microfluidic chamber and actually have an exchange of nutrients and wastes. So without the exchange of nutrients and waste, so we were able to put cells in it. And the nice thing about it is this structure is that you can, this is work in collaboration with Professor Jun Kong here in chemical engineering. So he provided us various materials, and these essentially are more or less commercially available, but you can characterize this, and the nice thing is that you can change the molecular weight, and of course you can change the elastic modulus. So you could have different layers with different elastic modulus and different stiffness in different vertical layers of the structure. And then we can keep cells alive, and this was the nicest part of the results, where we can keep cells alive up to 2 weeks. So what you see here is relative cell viability. In this case, these are 3 T3 cells, and what you see here is the different molecular weight. So the larger the molecular weight, certainly the cells stay alive longer because the cells have room to grow and move around and the material is not as stiff. When the molecular weight is low, that's a 700 or so, then cells don't stay alive for very long. Each one of these bars is over different days. You go from day 0 to day 14. The green one is day 14. And you can clearly see that in the case of PEG 3400 with this RGDS peptide, this is a peptide sequence that is linked to the polymer, and it actually helps cell to bind, provides these adhesion sites for the cells, so that the cells can actually grow and proliferate even more than they would. So you definitely need this RGDS peptides in these molecules to get the cells to stay alive and grow. They will stay alive, but they won't grow without this. So you can see that the cells certainly stay alive for 14 days, and in some cases with the RGDS peptides, they even increase above the 100%, which was the starting number. So with 700, they died the next day. Day one, all the cells were dead. With 700 plus RGDS, they stay alive for a little bit longer. With Tech 3400, they certainly stay alive up to 2 weeks, but they don't grow or increase in number. And then with Tech 3400, with the RGDS, they actually increase in number, so they actually grow, essentially. And these are fluorescent image and confocal images of these cells. The green is live, red is dead. So the more green dots, the more cells there are that are growing, you can see the cells are actually alive. And here's some images of cells actually spread within this polymer. So now with this, let me show you a couple of applications very quickly. And I can certainly go on in the next one too if you want to stop, let me know. But I have a couple of slides I'll show. So what we wanted to see here is to make, and this is a collaboration with Professor John here in chemical engineering, we wanted to see if we can make a scaffold that can direct formation of blood vessels. So angiogenesis is a process that is the process for formation of blood vessels, and we want to see if we can actually direct that using a pattern from living tissue. So now you're not talking about patterning solid structures, we're talking about patterning blood vessels. And if you can direct the formation of blood vessels. So we form a structure like this, which is essentially a circular disc that's about a centimeter, or a little over a centimeter on the side. And it has these pores in it. And these are large. They can range, we made them from 300 microns up to almost a millimeter, to 1,000 microns. And we put these pores inside the hydrogel structure. And this hydrogel structure that has cells in it, it has embedded cells, and the material composition is controlled. So the stamp, this microvascular stamp, we call it cells that secrete pro-angiogenic factors, and they have different patterns for directing the growth. So I wanted to then see what we can do with this. So I'll skip this actually. And then we took the structure and put it in what's called a CAM assay. It is a chick chorioallantoic membrane assay. CAM assay. This is the most widely used assay actually for drug screening, where you use a chick embryo. So this is an egg. You crack open the part of the egg here, and then this is your actual embryo in there, and then you put the gel structure there. That's what we did, and then incubate over time and see what happens in that region. So they actually put the structure inside an egg, and this is the broken shell. We put our structure there, and then we look at it over time, over the 14 days. And what's very, very interesting is that, so this is the implant of the stamp in the CAM assay. This was the stamp right there. You can see it, right? Everyone can see it. And this is a different material. This is PEG 1000. This is PEG D8000, PEG D8000 with actually alginate, and this is the PEG D8000 alginate with the microchannels. You can see the microchannels right there in that structure, right? So what's very interesting is that after 14 days, after a week and 14 days, when we take this out, we can actually see the blood vessel forming patterns around this, where the holes were in that stamp. And that has to do with the angiogenic factors diffusing out and creating a concentration gradient and directing the growth of the blood vessels in those regions. So this is the stamp has been removed, and you can see the blood vessels have been formed in a square region, essentially. So we're very excited about this result, and we're trying to move this forward. The idea here would be that if there's a injury or a scar someplace, let's say in a heart or some other organ, and you want to direct blood vessels to that region, you make the stamp and you implant it there surgically, and it could direct blood vessel formation there. So this is an example of this. And here you can see some more data. What was very interesting was that the pore size has to be actually in a certain region. If you make them too small, then you don't form the microvasculature dictated by the pores. It has to be about 800 or larger, and then you actually form it, and then you do the diffusion. We're also working on trying to put this in a rat infarct model, this is a rat heart, a magnified picture of a rat heart, working with Professor Rashid here on campus, and he has this, they've created an animal model where you can do a surgery on a little rat and then actually create a little heart attack, essentially, by closing an artery, by closing this coronary artery. You actually suture it, so you close the blood flow, you create an infarcted region, which is essentially a heart damage, a heart attack, and then the idea is to put the stamp. We haven't done, we are working on doing this, put the stamp on, and then see whether the stamp, the placement of the stamp within the other pores will actually help to recover that damage faster versus other cases. Okay, I think I'll stop right here, and I can continue on this actually after the break. We have some more time. Okay.